Ari, Ben, Cam, and Dan have booked a flight to Florida. The airplane has 4 seats in each row, and they are planning to sit in the same row. What is the probability that Cam and Dan will be sitting on the same side of the airplane? And I thought this question was a little confusing because I was wondering, do they know what row they're sitting in? Is that kind of something we have to take into consideration? But if you read it carefully, it says they are planning to sit in the same row. So we know they're going to be sitting in the same row, and it's just a matter of arranging who's sitting on the left side and who's sitting on the right side. Okay? So we're gonna use things we learned in the counting methods unit to come up with some of our favorable outcomes and our total outcomes. Because remember, when we're talking about probability, we're talking about favorable outcomes over total, right? So our favorable outcome is when Cam and Dan are sitting on the same side of the airplane, okay? So how many different ways can Cam and Dan sit on the same side of the airplane? Sawyer, you said 4? How many different ways can Cam and Dan sit on the same side of the airplane? So if you just look at the first row, we're just going to look at one row, right? So we have A, C, D, F for some reason. How many different ways can Cam and Dan sit on the same side? You could ask that, and that's maybe you're joking, but that is something you can do later on. Okay, that's good. That's good. 2, you say 2. So what are the 2? We can have like Cam and Dan sitting on the left and Cam and Dan sitting on the right. Now what if you switch? What if Cam is sitting in the window seat and Dan sitting in the aisle seat, right? And then you can switch Dan sitting in the window seat and Dan sitting in the aisle seat, right? So you can reason like that to find that there's 4. There's 4 favorable outcomes. Um, yeah. So we'll just say we have 4 favorable outcomes. How many total outcomes are there? So why do you say 8? Yeah. Okay. Yeah. So you also include these ones here, right? Yeah. So this is when we can use what we learned last unit. So we've got 4 different positions, right? So I'm just going to write that here. And 4 different people. So how many choices do I have in the first one here? 4, exactly, right? And the second one? Right, because someone's already sitting down. And then 2 and 1. So that equals 4 factorial, right? And what is 4 factorial? Maybe you haven't memorized by now. 24, good, okay? So our probability is 4 out of 24, which we can simplify to 1 over 6, okay? And we used counting methods to find this. So if you thought we were out of the woods when it came to counting methods, we're not. So things to remember, the fundamental counting principle. What is a fundamental counting principle? Remember, when you use the word and, when you're making a few different choices, you can multiply them, right? That's the fundamental counting principle. And it's just they're reminding you about permutations and combinations at the bottom there. So remember, when order matters, we use permutations. When order doesn't matter, we use combinations. So let's move on to example 1 here. Jamal, Ethan, and Alberto are competing with 7 other boys to be on their school's cross-country team. All the boys have an equal chance of winning the trial race, which isn't really how it works in reality. You don't really have an equal chance. Yeah? If Okay, and I guess I mean like, because everyone's got different strength, right? Everyone can run differently. But okay, so let's just assume that they have an equal chance of winning. Determine the probability that Jamal, Ethan, and Alberto will place first, second, and third in any order. Okay, so it tells us right here in any order. So does order matter? No, in any order, right? They can finish in any order. So again, we're going to have favorable over total. Okay, favorable over total. Okay. How many total runners are there? Well, so we've got Jamal, Ethan, and Alberta are competing with 7 other boys. So there are 10 total. Okay. How do we find the number of favorable outcomes? How do we find that? Sorry, Kristen? Okay, so either one can be first, second, or third. So what do we do when order doesn't matter? Right, the choose one. So we're going to use choose for the favorable outcomes. And what is our total pool? Okay, this is kind of interesting. So what is our total pool? How many people are competing? 10, right? So 10 people are competing, and how many are we choosing? 3. So remember, this gives us a number, okay? When we do 10 choose 3, that gives us a number. That gives us a number of outcomes, number of favorable outcomes in this case. Now, how do we determine the total number of outcomes? So Jesse, what did you say? And why do you say 10 factorial? Because there's no restrictions, okay. And right. So in this case, order does matter because we are going to end up having a first, second, third, all the way to 10th place racer, right? So in this case, order does matter. And again, you can use a strategy like this, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, just to help you visualize it, right? This is our first place, and this is our second place, or sorry, 10th place. And you can think, okay, there's 10 possibilities there, 9 here, 8, 7, 6, 5, 4, 3, 2, 1. And you can multiply those all together. You get 10 factorial. Can anyone tell me what you get for this here? Like that, Jesse? Okay, so 3 million, right? Is this right? Okay. Yeah, I heard a few sixes. So 120 out of about 3 million. So that's the probability. Sorry, Kristen? It doesn't make a nice fraction, and that's okay. That's okay. So this is our probability here. And it might be a bit confusing to remember, like, when do I use combination? When do I use permutation? When do I use factorial? And it does take a little bit of thinking and a little bit of reasoning. So really take your time with some of these questions. If it seems complicated, take your time with it. And think about your different favorable outcomes and your different total outcomes, right? Are there any questions about that example? Okay. This is example 2. About 20 years after they graduated from high school, Blake, Mario, and Simon met in a mall. Blake had 2 daughters with him, and he said he had 3 other children at home. Determine the probability that at least one of Blake's children is a boy. So we have the word here, at least. 3 and 6, like 3 over 6. Is that your guess? Yeah. Right, because you've got a choice of 2, 2, and 2, right? So, but yeah, let's work this out here. Favorable over total. Okay, and I think the favorable outcome is harder to figure out in this case. Um, so we've got those two words at least, right? So we know that we have a few different cases. So we can have, if we're having at least one boy, we can have boy, girl, girl, boy, boy, girl, or boy, 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 right? So these are our three different cases. Um, so we want to choose for the B here, for the boy. Give me just 1 second. All right, guys, so I kind of suspected this. There's a little bit of an easier way to work out this question. Um, so let's first find our total number of outcomes. So there's 3 children, and how many different choices do we have for each child? Boy or girl, right? So we've got 2 for each child. I guess we're assuming that it's either a boy or a girl. And that gives us 8. Right. So this is our total, right? So we're not talking about our favorable outcomes. This is our total, right? Because they're asking here, determine the probability. So whenever we're determining the probability, we know that we're going to have favorable over total. And in this case, it's a favorable outcome when there is one boy, right? So when there's at least one boy, that's favorable. That's what we're determining, right? But our total outcome is this here, our 8. That's how many different combinations there are of children. And you could list them all out if you want. Boy, girl, girl, boy, boy, girl. So what we're going to do here, we could have gone through all those different cases, but remember that if we have all girls, right? What is a probability that we're going to have all girls? So if we list out all these different, so we've got boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy. Okay, so if you did do this, you've listed out all the different combinations of children for Blake, right? Um, and you can see that any of them with at least one boy is favorable. So, for example, this one has 3 boys, so this is okay. This is good. And same with this one. All of them, right? Except for the last one, which this should be a girl here. So in a case like this, you can list them all out, or you can determine if we've got this last one here, we know that girl, girl, girl is a 1 out of 8 chance, right? That our probability for a girl is 1 out of 8. You said that? Good. And if we know that our probability of having all girls is 1 out of 8, how can we find the probability of having at least 1 out of 8, right? So this is like our probability of not A is 1 out of 7. I'm sorry, 1 out of 8. Listing it out like this. So if we have a probability of not A and it's 1 out of 8, what is our probability of A? So it's a complement, right? If our probability of not A is 1 over 8, our probability of A, we talked about this briefly yesterday, is 1 minus our probability of not A. This is the relationship between probability of A and probability of not A. So our probability is 7 out of 8. 7 out of 8. That at least one of Blake's children is a boy. Are there any questions about that? That one's a bit. Just move on. Okay, example 3. Example 3. Bo hosts a morning radio show. Actually, can you see from there? Yeah? Okay. Bo hosts a morning radio show in Saskatoon. To advertise his show, he is holding a contest at a local mall. He spells out Saskatchewan with letter tiles. Then he turns the tiles face down and mixes them up. He asks Sally, so Sally is a contestant, to arrange, or his assistant, he asks Sally to arrange the tiles in a row and turn them face up. If the row of tiles spells Saskatchewan, Sally will win a new car. Determine the probability that Sally will win the car. So, you can imagine we've got all these different tiles that are the letters for Saskatchewan. And let's start with total again. Remember, we've got favorable over total. And how are we going to find our total number of outcomes? This is like the question we asked in last unit. When you have repeating letters, how do you find the number of different combinations? Or how do you find the number of different sequences, right? Because there's 3 A's, that's good, yeah? And then, yeah, because there's 2 S's, right? Times 2 factorial. So this will give you your total. That's your total number of outcomes. And so this is your total. What do you get for this? Do you guys mind calculating that? Or I can look here. Yeah, you should use brackets when you're dividing. One 400. Okay, so this is 119 million about? No? Yeah. Oh, so you got a minus there. You can multiply. No worries. No worries. That's okay. So, anyone else? 16800. So that's about 39 million. So there are about 39 million total outcomes. Okay, total. And if we want to find our favorable, if you want to find your favorable, let's just take a look at it like this. We want to spell the word Saskatchewan. Okay, so how many choices do we have for the first letter here? We want to spell the word Saskatchewan. If it's a favorable outcome, we want to spell Saskatchewan. So why do you say 1? You're right, it has to be S, but we have 2 choices for the S, right? So this can be a 2 here. How about for the next one? 3, exactly, because we're choosing an A and there are 3 different A's, right? Yeah. And then 1, 1, 1, 1, 1, 1, 1. And if we multiply this together, what do we get? 12. Okay, so there are 12 favorable outcomes. Okay, this is favorable. Not at all. This is, yeah, they're really bad chances to win this game. So this is 12 over about 39,916,800. Okay? Yeah. So for questions like these, remember you really have to think about how do I count the number of favorable outcomes, right? So it's like you have it's really narrow sometimes, this favorable outcome. There aren't a lot of favorable outcomes. And then she wins a car. So let's look at example 4. There are 18 bikes in Marnie's spinning class. The bikes are arranged in 3 rows with 6 bikes in each row. Allison, Brett, Carol, Doug, Erica, and Franco each call the gym to reserve a bike. They hope to be in the same row, but they cannot request a specific bike. Determine the probability that all 6 friends will be in the same row with Allison and Franco at either end. This is really specific, isn't it? So again, remember we're doing favorable over total. And let's start with our total. Okay. So we have 3 rows of 6 bikes. So we've got 18 bikes altogether. And in this case, does order matter? Yeah. So in this case, order matters, right? So we know that there's going to be 18 people in the class and that there are 18 bikes. So how can we find the total number? So you can imagine if I wrote out 18 lines here, how many choices would we have in the first place? 18, right? Yeah, good. So we have 18 factorial total outcomes. I should really have my calculator here. Too much? All right, guys, don't worry about example 4. We're not going to do example 4. That was your answer?